Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our previous session, we have discussed about the Gated Recurrent Unit, GRU, its architecture and working. In today's session, we will speak about LSTM, encoder-decoder structure. So the contents for today's discussion goes like Introduction to Encoder-Decoder Architecture, Encoder LSTM, Decoder LSTM, Teacher Forcing Method, Training and Inference of Decoder, Limitations of Encoder-Decoder Architecture. So we will first have a look into the motivation for an encoder-decoder LSTM. What was the need for encoder-decoder LSTM? A single LSTM is a network that processes a sequence and produces outputs within the same sequence. Now let us understand what do I mean by this statement. Suppose I have a sentence, I love this movie, and I am passing it through an LSTM for sentiment analysis. That means whether this sentiment is having a positive sentiment, negative sentiment, or a neutral sentiment. So the output will be positive. That means the sentiment of this sentence is positive. Now this is an example where the input and output, the relationship between them is many to one. So I love this movie. There are 4 words in this input sequence and the output is 1 word, okay, which we call as token in natural language processing. So it is a many to one, mapping. Now take another example. I love NLP. You are passing it through an LSTM structure and you want the parts of speech tagging for this sentence. Now, parts of speech tagging will give the first word I as pronoun, then the second word love as verb and NLP as a noun. So, this is an example of many to many. That means the input sequence and the output sequence, there is a many to many relationship and they are aligned. That means the first input is aligned to the first output, second input is aligned to the second output, third input is aligned to the third output. So, this is called many to many aligned relationship or sequence. Now, take an example of a machine translation. That means I want to translate an English sentence into French. Suppose the English sentence is she is reading a book. She is reading a book. So, it has 5 words. When I am doing a machine translation, the French is say liest en butch. So, it is having 4 words. Okay. So, there is a mismatch or the number of words in the input sequence is not matching with the number of words in the output sequence. So, these type of tasks are known as sequence to sequence modeling and they can be handled by encoder-decoder LSTMs, which are not possible by vanilla LSTMs. Okay. So, we will see what is this encoder-decoder LSTM. Now, we will look into the architecture first. So, we have an encoder. We will go into details later in my next slide what is there inside the encoder, and then we have a decoder. And both encoder and decoder are made up of LSTM structures. Okay. So, the input sequence goes into the encoder. Then from the encoder comes out some states. What are these states? These are hidden states and the cell states. And these states, they have the compressed information from the input sequence. So, whatever is your input sequence, the full sentence, it gets compressed and the information is carried in the states. And then we have these states going to the decoder and decoder gives an output. Decoder gives an output. Okay. So, the encoder takes the English sentence, the decoder gives the French sentence, the translated one. Okay. Now, we will see in details what is there in the encoder-decoder architecture. So, we have an LSTM. The input at time step 1 is x1 and it is also getting input from the previous time step h0 and c0, which is the hidden and cell state from the previous time step, and then this LSTM is giving an output hidden states and cell state C1 and H1. It is going to the second LSTM. Second LSTM is getting another input which is x2, which is the input at the second time instance, and this continues for x3 also. X3 is the input at the third instance of time. So, the LSTM, the third LSTM gets input x3 and H2 and C2 from the previous LSTMs, which is the hidden state and the cell state, okay, H2 and C2, and then this goes, the output of this LSTM is H3 and C3, and these goes, this output states, they form something called as the thought vector. Now, this thought vector is basically having all the information of the input sequence, whatever we have given in the form of x1, x2, x3 words, that is getting compressed and that is present in this thought vector. And this thought vector is going to again some LSTM, and which is giving an output y1, and this is followed by another LSTM giving an output y2. So, what happens is this entire left hand side is the encoder structure, entire right hand side is the decoder structure. So, what we see, encoder and decoder both are made up of LSTM structures, where LSTM takes the input from each time step, the input sequence and the hidden and the cell states from the previous states. Finally, it gives the thought vector, which is having the compressed information, which is going to the decoder LSTMs, and the decoder LSTMs gives the output y1, y2 and so on. Now, we will see how the encoder LSTM works. So, we have seen here, I have missed the C0, just a minute. So, here it will be C0. Okay. So, we have seen this structure in the previous slide itself, and then what is this xi? Xi can be x1, x2, x3, x4, anything. This is my input sequence at time step I. It can be a word embedding, a mathematical form of a word, or a feature vector. HIs are basically, they are the hidden state at time step I. Ci are the cell state at the time step I, and yi, basically y1, y2, y3, y4, etc., they are the output or prediction sequence at time step I. Okay. So, these are the things that consist of my encoder structure, encoder LSTMs. The outputs of the encoder are discarded and only the internal states are preserved. So, that means whatever is coming out in the form of y4, yk, y3, y2, y1, we are not taking it to the decoder, we are discarding them. Only whatever is going to the decoder is your hk and ck. And this hk and ck, which is the hidden state and the cell state at the kth time instance, it is having the encoded summary of the input. Okay. So, that is the thing which is going to the decoder. Now, we will see an example. See, suppose my input sentence is Orna is a good student. Okay. So, this is my x1, this is my x2, this is my x3, x4, x5. Okay. Now, whatever outputs we are getting in the form of y1, y2, y3, y4, y5, these outputs of the encoder we are discarding. We are not taking them forward for processing. The final states of the output summarizes or encode the entire input sequence through the thought vector. Okay. Now, H0 and C0, they are initialized to 0 as the model has not started reading the input. So, H0 and C0 will be equal to 0. Hi and Ci, these are the hidden states and the cell state of the LSTMs. So, LSTMs maintain two states, the hidden state and the cell state at each time step, and combined together are the internal states of the LSTM at each time step I. Okay. They remember what is the function of this Hi and Ci. They remember what the LSTM has read till now. Like for example, H3 and C3, if we take here, this vector remembers that network read Orna is a. Till this one, it will remember. Okay. So, H3 and C3 will remember till whatever it has read, it will have that memory. Okay. Now we will look into how the decoder LSTM work, what is there inside the decoder, and so on. The initial states of the decoder LSTM are initialized to the final state of the encoder LSTM, because from the encoder LSTM only it is going to the decoder LSTM. So, the initial states of the decoder LSTM are initialized to the final state of the encoder. So, we have a token which is called as the start token, which is always present as the first token in any sentence when we are processing it through decoder LSTM. So, the start token goes to the LSTM. This is an LSTM block, and this is getting inputs H0 and C0, which is these are the states, output states of the encoder. So, basically here H0 and C0, these are the output states of the encoder. And then this whatever output is coming, it is going through the Softmax. I will tell in my next slide what is the function of the Softmax. After the Softmax, it gives the first translated word. In this case, I have taken an English to Hindi translation. So, start, and once the states of the output states of the encoder are fed into this LSTM, it gives the, after Softmax, it gives the output Orna in Hindi alphabets, and then this is Y1 output, and then from this LSTM again H1 C1 goes to the next LSTM, and this comes here as the input, and after the output of this LSTM goes to Softmax, and we get the output prediction Y2, which is ek, which is the Hindi of Orna is a good student. Orna is a good student. So, Orna ek. Then again the output of this LSTM goes H2 C2 goes to the next LSTM structure. Here this comes here, basically this comes here, ek, it takes the input here, and together with H2 C2 and this input, this LSTM gives some output which goes to the Softmax and gives Y3, which is Achhi, which is the Hindi of good, and then the output of this LSTM H3C3, the hidden and the cell states, goes to the next LSTM. This Achhi then comes as the input to this one. So, basically this will come as the input here, okay, and then the output again goes to the Softmax, and we get the prediction Y4 Chhatra, which is student, and again the output cell state and hidden state of this LSTM goes to the next LSTM, and this comes once again here, and same thing after Softmax we get Y5, which is the prediction, and we get hai. So, Orna ek achhi chhatra hai. So, Orna is a good student. So, this is the translation of English to Hindi with the encoder and decoder LSTM. So, this is how the decoder LSTM decodes it. It takes the input from the encoder's final states, the cell state and the hidden state, and then it passes through LSTM structures at various instances of time, and then it starts with the first start token, and we will see at the end, when the end of the sentence is reached, we get the output token as end. So, this is the prediction, the last prediction, which means it is the end of the sentence. Okay. So, this is how the decoder LSTM works. So, each and every step, it takes the hidden and the cell states from the previous step. It takes the output from the previous LSTM decoder's LSTM structure, and then this one goes as the input here, this one also goes as the input here, and so on and so forth. Okay. So, this also goes here. So, this is how the decoder LSTM decodes whatever the encoder has given the information. Okay. Now, two tokens start and end are added to the output sequence. So, we are adding start and end in the decoder LSTM's processing. to say to the model that this is the start of the or the beginning of the sentence and this is the end of the sentence. Okay. Now we will come into function of softmax in the decoder LSTM. What is the softmax function doing there? So I have kept that same figure here once again. YIs are the predictions of the decoder LSTM model at each time step, okay, I, each time step I. So the thing is, so Y1, Y2, Y3, Y4, Y5 and Y6, these are the predictions of the decoded LSTM. And each YI is actually a probability distribution over the entire vocabulary which is generated using a softmax activation function. Now this Y1, how exactly it is generated? So Y1 is actually a probability distribution over the entire vocabulary. Entire dictionary of words, whatever is there, there is a probability distribution of this output over the entire vocabulary. So each and every word in the vocabulary will get a probability, and this probability is generated using the softmax activation function. We know softmax activation function gives values between 0 and 1, which is actually the probability. So whichever is getting the maximum probability, that is coming out as my yi. Okay. So that is how the softmax is playing a major or significant role in the decoder LSTM. So it is whatever information it is getting from the encoder together with the previous states of the decoder LSTM, whatever predictions it is it is having, it is basically a probability distribution of predictions, probability distribution over the entire set of words in a vocabulary, and whichever word is getting the highest probability, that is given as the output in terms of Y1, Y2, Y3, Y4 or Y5. Okay. So that is how the decoder LSTM works, and it takes help of the softmax activation function. Now there is a new term which we will learn here, which is teacher forcing. Now we will see what exactly it is. Suppose we are trying to do an image captioning task. So we have an image and I want my structure, my model to do an image captioning work. So I have this picture. So there are two boys and they are playing cricket in a village. So the caption, the best caption can be two boys playing cricket. So this is the caption, okay, which I want my model to predict, okay. I give the image and the model should give me two boys playing cricket as the caption of the image. Now, here what happens? We have the encoder output. We know whatever feature vector or feature map we give to the encoder, at the end of the encoder we get the information in a compressed form, and that comes in the encoder output. This encoder output goes to the LSTM, and then there is a start token at the beginning, and suppose Y1 is your prediction, it gives first based on your input image, the first word it has predicted is 2, which is a correct prediction. Then it is going to the next LSTM, your hidden states and cell states here, and this 2 is coming as the input to the next LSTM, and your Y2 actually the prediction of this Y2 word or Y2 prediction becomes bird. Instead of boy, it becomes bird, which is basically a wrong prediction. There are no birds here which are there and which can come in the caption of the image. Now what happens? If we continue with this one, when it is going to the third block, what happens is, third instance, this bird comes as the input to the third block LSTM, and then Y3, whatever is predicted based on your previous cell state and hidden state and this input bird, the Y3 prediction now becomes flying, and then it continues. So what happens here is, normal decoder, this is the normal decoder, how it works without teacher forcing. We have not gone exactly into what is teacher forcing. This is to say what is the limitation of normal decoder. So in normal decoder training without teacher forcing, the mistake in the prediction of one word affects the entire prediction of the image caption. Okay. So, if we continue with this one, the bird's input goes here, and then based on the birds it is predicting flying. It cannot predict playing cricket, okay, based on the bird input. So, then the mistake in the prediction of one word affects the entire prediction of the image caption. Okay. So, we will see now what is this teacher forcing. So, in teacher forcing, what happens? Whatever we have the encoder's output, it is going to the first block, and then we have the start token, and the prediction is y1, which is your 2. Then the cell state and the hidden state from this LSTM goes to the next LSTM, and here this 2 once again comes here, but what we will see here, the difference here is this is basically whatever we are giving as input to the second, third, fourth LSTM blocks, they are the ground truths. We are not giving the predictions as the input to the LSTM. So, here this 2 is actually coming from your ground truth, and then suppose the same thing is having your y2 prediction is bird, which is once again a wrong prediction. But then what happens is, because we are not taking this bird as the input to the next LSTM, I am taking the ground truth, which is actually the boys. Okay. So, that goes as the input to this LSTM block with the hidden and cell states coming from the previous LSTM block. So, my y3 prediction becomes playing. So, only one prediction is wrong, but the third prediction becomes correct, and once again this playing goes here, which is from the ground truth set, not from the predicted one, and then we have the cell state and hidden state coming from the previous LSTM blocks, and we have the y4 prediction as cricket, and then the cricket once again from the ground truth comes as the input to this LSTM with the hidden and the cell state from the previous LSTM, and then we get a Wi-Fi, which is the end token. Okay. So, this process is called as teacher forcing. That means we are giving the ground truth as the input, not the predicted output to the LSTMs of the decoder. Okay. So, during training time of the decoder, the input at each time step to the decoder are the actual output and not the predicted output. Okay. So, these are the ground truth of the previous time step. This is called as the teacher forcing. Okay. This is called as the teacher forcing method. Okay. Now, we will look into the decoder LSTM with the same example. So, here H0 and C0, these are initiated to the final states of the encoder, and whatever output we get from here, decoder is trained to. Now, the question may come that how is the decoder getting trained to predict the outputs? Decoder is trained to generate outputs at each time step through backpropagation and using appropriate loss functions. So, this is during the training time. So, we were giving based on the final state of the encoder, the start and the start token, we got this term orna, and then this was, and all these things were coming from the ground truth. These all orna ek achhi chhatra hai, these we were using for training the decoder, and the decoder is trained to generate the output at each time step through the backpropagation using an appropriate loss function. Okay. So, these are all the ground truths. Okay. And then it gets trained. Okay. This is the way the English to Hindi translation should happen. The final states of the decoder are discarded during the training phase. So, this is the training phase of the decoder. Okay. So, the final states we are not doing anything, we are just taking the predictions from each and every time step. Okay. Now, inference from the decoder. What happens during the inference time? This whatever I have shown till now, it was during the training time. What happens during the inference time? During inference time, there are no ground truths. Hence, the predicted output is given as the input to the next sequence. So, here what happens is encoder output is here, then you have the start token, then y1 is 2, that 2 boys playing cricket, so like that. Now, this one was going here as the input, and then y2 is given based on this input, and this boys is coming here, and y3 is the output from this sequence playing, and then this playing comes here, and this is also as taken as an input. So what is happening here is all the predictions here are coming as input to the next time step. So the 2 predicted here in the first time step becomes the input for the second time step, together with the hidden and the cell state from the previous layer. The second time step output becomes the input for the third time step, and third time step's output becomes the input for the fourth time step, and so on. Okay, and then finally it continues. So 2 boys playing cricket. So whatever outputs we are getting, that is coming as the input. So this happens during the inference time, because during the inference time we don't have any ground truth to be shown. So we have only the image, the encoded output from the encoder, and based on that one is your caption is getting produced. Okay. Now, so if we see the encoder decoder architecture, so this is basically your encoder architecture. Orna is a good student. So this is your encoder, and encoders, each time step inputs were going on like this, and these are the various LSTM blocks, and these are the outputs of the encoder. Okay, and discarded, these outputs are discarded and they are not taken forward, only the states, the hidden states and the cell states are taken forward. And then we have this one, we have the entire thing, the start token, the states goes to the decoder, and based on that one you get y1, y2, y3, y4, y5 and y6 predictions. Now start and end token gives you the signal that this is the beginning of the sentence and this is the end of the sentence, and the states give you the compressed information from the encoder to the decoder. Okay, so this is the decoder, this entire thing is the decoder, and this one is the encoder. So this is how the encoder's input is going to the decoder through the cell state and hidden state output of the encoder. Now the decoders, the final states, that is the decoder states, that is the cell state and hidden state at the last time instance, they are discarded. We don't take them for any further processing or for any information to be derived. What we are taking from the decoder is only the predictions y1, y2, y3, y4, y5, y6. Whereas in case of encoder, it was we were discarding the outputs but taking forward the hidden state and the cell state. Okay. So this is the encoder decoder architecture. Now what are the limitations of encoder decoder architecture? Encoder steps need to represent the entire input sequence x1, x2 to xn as a single vector C. This may cause information loss as all information needs to be compressed within C. Decoder needs to decipher the past information from this single vector, which is a highly complex task. So, what are the limitations? As if we have a very long sentence, so there are a lot of words or lot of tokens, we call it in natural language processing, the tokens. So, if it is a very long word of say 10 to 12 words, a long sentence with 10 to 12 words, then what happens is your decoder output, it is only one vector which is having the information or compressed information of the entire sequence, all the 12 words. Now, due to this compression, lot of times happens is that there is an information loss because of this compression, and for the decoder also to decipher this past information from a single vector, it becomes a complex task. So, and in this when this happens, there can be there are places where we or the model will not be able to give attention to the words and which are required to be given attention, and then it may lead to some wrong predictions. Okay. So, what is the solution for that one? Solution is attention mechanism. So, attention mechanism in LSTMs is the topic for my next discussion, next lecture discussion. So, I will come to an end of this today's lecture. let us quickly summarize what we have learned today. So we have seen what is the motivation for this encoder-decoder architecture of LSTM. So we have seen what are the cases where our normal traditional LSTMs cannot handle, like machine translation, where we are changing from one language to another language. There is a sequence to sequence modeling is required. The input sequence length may not match with the output sequence length. They may not be aligned also. So these are the cases where our encoder decoder architecture comes into picture. The encoder decoder architecture consists of the encoder and the decoder. The encoder gives all the information from the input sequence in the form of the cell state and the hidden state to the decoder, and the decoder decodes or deciphers that information, and it takes it takes the input of the encoder's output, and then it starts decoding. And then we have seen how the decoding has happened in the decoder during the training time, when we are training the decoder, and when we are taking inference from the decoder, the processes are different. So when we are training the decoder, we use a process called as teacher forcing method, where we use the actual output or the ground truth words for training the decoder. That means the ground truth words go as input to the LSTMs and not the predicted outputs. Okay, because if during the training itself we take the predicted output to guide the next predictions, whenever if there is something wrong prediction happens, the entire process gets that wrong message, and finally the predictions become inaccurate. So for that one, teacher forcing method is the one in which the input to each and every LSTM block in the decoder, they get the input from the ground truth as well as the hidden state and the cell state from the previous LSTM structure. So this is the difference between the decoder training and decoders use during the inference. During the inference, we don't have the ground truths. So whatever it is predicting, that prediction only is coming as the input for the next sequence, and together with the hidden and the cell state from the previous step. So this is how the decoder is trained. And then we have seen the encoder's outputs are discarded, whereas for the decoder, the hidden state and the cell state are discarded, and the predictions or the output sequences are taken into consideration for the predictions. And we have seen how Softmax activation function helps the decoder to give a probability distribution across all the words in the vocabulary and take out the most probable choice for the output prediction. Okay. And then we have seen what can be the limitations of this encoder decoder architecture. As we have seen in the encoder, the entire input sequence is compressed and we get the thought vector which goes to the decoder architecture. So it is a compressed form of a long sentence, due to which there may be some information loss. Now for the decoder also to decipher the entire information from the only one vector is a challenging task. And due to this one, lot of times what happens is the predictions don't become accurate. And what is the solution to that one? That the solution to that one is attention mechanism, and which is what is the topic of my discussion in my next session. So I hope you all have understood how the LSTM encoder decoder structure works, and how the translations and other things are taken care of in encoder decoder LSTMs. In the next session, we will talk about LSTMs with attention, and till that time, please keep learning. Happy learning. Thank you all.